work on NS3 and especially the one on LENA that we started as Jesus said a few years ago, and which is a quite productive and interesting solution. Let me just see whether I can use what this? Oh, okay. Does it work or not? Well, I can use the keyboard.
No, but it should work.
Well, we can check.
The pointer is working.
Well, at least the pointer,
Is this
if I
right?
need it. Probably it's with the Acrobat Reader that is not working. I don't know, but it should work.
Yeah, it should work.
It's not. Well, you can check it.
Well, at least you have the pointer.
If I need it. Okay, so let's start. So thanks, Jesus, for presenting me and for giving me this opportunity. So we will start introducing a bit NS3 in general, and then we move to LENA, this project that we are carrying on in CTTC since 5 years ago. So the first part will be starting on NS3. So what is NS3? So let's take a step back. So from testbed to simulator, ready to return. So we are going a bit on the other side, but it's okay. So on this, NS3 is a simulator. So but not only a simulator, let me just introduce you. So it's a discrete event simulator. So what does it mean? It means that it's just a simple list of events that you can generate, or you can directly generate, or either your algorithms or your network devices or your protocol can generate. So it's just a matter of let's say a list of events that has been processed. So it's important to understand this in order to understand how this network simulator works, because it's quite different from MATLAB. Since everything is triggered by events. So it's a network simulator. So it simulates the complete communication system, so from application to physical layer. Of course, it has a simplified physical layer model because we need to be not so much complex in order to do not have large simulation time. And but of course, what is the most critical protocols are detailed models, such as the one from MAC layer up to application layer. So in general, for instance, from Wi-Fi or LTE up to TCP, the model are very, very detailed. The model granularity in this case is from NS3 is the packet. So everything is the whole communication stack is designed around the packet, which is different from typical link level simulator, where you usually to work per symbol level, so working with code stream or either directly with bits or symbols. And even different from system level simulators, where usually the granularity is the radio frame. So you're usually to work only from MAC layer to below, to physical layer, and not only playing with applications. So in this case, we use packet in order to be comprehensive in the design of our networks. So it has a collection of simulation models. So trying to be as much comprehensive as possible, both from wireless and wired perspective, from protocols, application, from topology. So you can design very different topologies, mobility models, and propagation models. Of course, this probably many of you already knows also NS2, and since many people is still working on NS2. Of course, this is an extension of NS2. NS2 is not supported by NS3. Any protocol design on NS2 is very different from NS3. And this, of course, has been redesigned from scratch. So it is much more efficient, and especially from from programming language perspective, is much more, let's say, elegant respect to the NS2, since it has been redesigned from scratch from computer design people. So it's much more easy to understand. So what is NS3? Going forward, so we are talking about an open source software. So it is designed around the GPL versus 2 license. So the user are either networking researchers, but also educators and students. So the main idea is for academia, but during the last years also it has been adopted also by some companies. For instance, the work LENA started for a grant with a company, and also we are aware that many companies using LENA, NS3 in general, but also LENA, the one on LT. So since it's an open source project, it relies on an open source community. So it is developed and maintained by the open source community with a very active people. So you think there's a lot of people asking in the mailing list and providing answers in the mailing list, providing patches, providing new modules. It's a very active community. I don't remember the exact number, but it's quite huge, especially spread in the whole world. There's a lot of people working from US, from Europe, but also from Japan, and so on. Actually, we had the developers meeting last May here, and there's very wide, representative community. So this implies that critical bugs can be rapidly spotted and fixed, but also if you have any question, if you need some support, there is a very huge tutorial and people that can help you in answering. So let's move on. From my level perspective, it has a modular architecture, so it is easy to add new modules, and it's also easy to understand the modules, because thanks to this modularity architecture, it's aligned with real-world interfaces, especially with Linux. So when you set up your network, it looks like you are setting up a network in a Linux machine, more or less, with interfaces, with IP stack, and in application. And especially, so it has a huge emphasis on the real-world integration. So it's not only a simulator, but as I said before, it might be also an emulator. So one of the important things, respect for instance to NS2, is that it exchanges real packets. So when you create a packet from your routing protocol for sending hello packet, actually real bits are allocated in the memory, and these packets can be spilled off by, for instance, with pickup traces, and you can trace it with it. So this is an important feature for a network simulator. In fact, it can be used also for emulation mode, and also for tracking how the behavior of your simulation with standard tool like Wireshark. And especially, finally, you can integrate real code. So the emulation mode allows you to integrate, for instance, real application, VLC, Skype, and so on and so forth, and test in your network. So, important thing, it is written in C++, so no more like in NS2 different languages, TCL, C++. Now we have only C++, and it is very well written, let me say. So computer science people made very huge effort for providing some coding style issue, and now since all the code satisfy this coding style issue, it's a very well designed code. Optionally, you can use also Python bindings for setting up your simulation, but well, I'm not so familiar with this kind of usage. I would suggest to use C++. It has a very high optimized simulation core, so the packets are copy and write, so there's not this kind of weird behavior like in NS2 that packet can be exchanged without copying it. So usually the memory enlarged. This is probably very useful in IoT simulation. It is faster than the other network simulator. This is respect to some standard papers that in reference we have. The memory footprint is quite low, even in few cases, like for instance in the LTE, the memory footprint might be increased, but in general it's very low. It has an independent smart pointer implementation, so you do not have to be more scared about using pointer. So like in boot library, there is a very smart pointer implementation that allows you to play with pointer and do not getting crazy in understanding whether your pointer works or not, or there is a memory leak. And also, finally, there is an object framework that allows you to combine problems, or let's say in general entities in this object class, and this makes it easier to interact with this class, especially for instance, for connect objects or for configure this object. Oh, sorry. So the main modules are, of course, the core modules, which provides you the scheduler, the packet implementation, and so on and so forth. The network module for providing all the network interfaces, the internet stack, and the application. Of course, we have other module, for instance, utilities for tracking the performances, energy models, mobility models, and so on and so forth. What you can do with an NS3? So the idea is, as in a standard simulation, what we would like to do is to create different configuration, your simulation scenario. So interconnecting node in a network, running application in a network in order to generate traffic in the network, and finally get an output. So have some traces in order to check what is happening in your network and whether your algorithm works or not respect to the other. So what is an NS3 provide this kind of functionality. So the ability of configuring a network, run application, and then generate outputs for having traces, understand what is happening, also collecting measurements. So the architecture, as I said before, is very typical to the standard devices. Usually it's a standard PC, like the one with Linux. So the node architecture, what is called node in NS3, is like a bare-bone computer in which we have different network interfaces, Ethernet, Wi-Fi, LTE, and so on. We have the protocols, like, for instance, IP protocols, TCP protocols, and on top we run some application that might be standard browsing, VLC, and also Wireshark for having some traces. So it's very similar to a standard PC. When you create your node, it's just very similar as creating a node as your standard PC, let's say. For instance, node is a general structure. So as I told you, it can be a standard PC, but it can be either a router, or it can be either a laptop, or even an antenna, cellular antenna. So it's a very general architecture. Of course, you can, depending on what you plug in your node, you might have different configuration. So it is inspired, as I told you, the node, this important class in NS3 called node is inspired from real systems. So it's not just a matter of having abstract modeling. You actually have the node for supporting API and IP devices, driver interfaces in Linux. And you can use also part of the kernel and application code. And you can aggregate to this node other model, such as the mobility model or the energy model, in case you would like, for instance, to test movement, or you would like to test the energy behavior of your system. This is a typical example, a general example. So as you can see, we have the NS3 node class. We can have some traffic model, which can be either a general data application, video streaming, or HTTP, and so on and so forth, or a voice application. We have the routing protocol, the transport protocol, and routing protocols. So you have to set. And then at the bottom layer, we can have MAC and physical layer of the Ethernet of the devices. So usually are in MAC layer and physical layer, but might be something more simple in case of simple devices. And then we have the channels. Of course, each device has its own particular channel with its own particular specific propagation model. So this is the typical net device model. So going back, the net device is this kind of structure. So where you plug your actually wireless device. So Wi-Fi, LTE, Ethernet, and so on and so forth is the class in NS3 where you plug your device. So the available net device model that is already implemented in NS3 available is the point-to-point for having a simple connection, let's say, like an Ethernet connection, the CSMA, Wi-Fi, mesh point, WiMAX, LTE, and also a low-rate wireless PAN device. There is also some other one for simulating more, let's say, from high-level perspective, other networks. For instance, an ALOA, a standard ALOA, or some error network for testing just a simple connection with an error probability, or loopback connection for Ethernet devices, or the tap bridge, as I told you before, for collecting packets, for spinning out packets from the simulator. So this is moving on, from application perspective, there is a lot of applications, so you can play with the standard on-off, packet, UDP traffic, ping, UDP traces. So here you can you can create your own traces for sending UDP traffic. But this is the standard one. But of course, thanks to the modular architecture, it's very easy to write your own. If you would like to have a Poisson process generating packet, or a specific meter application that has a certain profile, it's very easy to understand. Also, you can use real application, and you can use NS3 in a real node with emulation mode. So using real application. From networking perspective, we have, of course, IPv4 and IPv6. So we are already, NS3 is already out ready for IPv6 simulation. The transport protocol are UDP and TCP, and NS3 is a network simulation cradle, which implies to use the Linux implementation of the TCP implementation of Linux machines. This is not so well supported, so what is usually used in NS3 is a standard TCP one. And also a very huge number of routing protocols that you can extend, also the click one in order to create your own. And there are many more, probably. These are the most, let's say, representative one. So what is, how we can model wireless network with NS3? So for modeling wireless network, we use the wireless device model, so Wi-Fi, LTE, and so on. So we can use the mobility model for keep track of the position and also to orchestrate the movement. So if we like to have specific mobility patterns in our scenario, we can program, we can actually create this sequence of movement. We have the propagation model. Usually the propagation model is plugged in the channel object. Usually the propagation model are device independent. So you can have, for instance, certain ITU model used either for Wi-Fi or LTE, since the propagation model is the same. Of course, you will plug it in different channels, because Wi-Fi is a specific channel, while LTE has another one. And the error model are defined per device basis. So depending on the device you're using, it might be that you have a very specific and detailed error model, like for instance in LTE, or a simplified version with, for instance, a disk model, or a simply Gilbert-Elliott Markov state, two Markov states in order to understand whether your packet is received correct or not. Move on. Regarding the propagation model, as I suggested, there is a lot of frequency flat propagation model, free Sturgeon ground, moving on ITU, the standard accumulator for cellular system. Also there is JX simulator, and you can define your own, especially with the matrices. So if you need to have a specific configuration and you would like to test how works your protocol with a certain signal strength topology, you can either define it with a simple matrix, for instance. And also there is some frequency selective models, especially the one on fading. You can generate frequency selective fading trace, which this is used, for instance, in LTE systems. So how to configure, when you create your own node in your own wireless network that we would like to simulate, you have, of course, to configure it. And in order to correctly configure it and easily do it, NS3 provides this attribute system, which is a very friendly way for configuring it. So each object has a set of attributes. The object class I told you before. So each let's say usually an object might be a routing protocol or a MAC layer. Imagine a MAC. So it has a set of attributes. So each attribute has a name, an help text, a type, and a default value. So you can control this value and by just checking in the simulation how they are defined. And this is, for instance, also defined in the documentation. The simulation parameters are controlled either by attributes or can be either set by command line, or you can use configuration files, and you can visualize it with a graphical user interface. So you can control what is happening in your simulation with this graphical user interface. So it's easy to verify whether you have been able to correctly configure a network or not. This, of course, is done in order to make more easy the life to developer and especially user that would like to manage configuration for a simulation campaign. So provide different setups. All this data regarding name, help, value, and default value are already integrated in the documentation. The NS3 provide a very friendly Doxygen documentation that you can just play with it and you can easily reach all the objects and have all the information regarding the attributes of the objects. So there is no an official graphical user interfaces for developing on NS3 and either for processing the data, but there's a few interesting tools. For instance, this one is the one I was talking before. This is the graphical user interface for checking the parameters. These are a few works for generating some network architecture that works, for instance, with Wi-Fi. And with LTE, they do not work very well. They have some problem for working with LTE, but with Wi-Fi they work rather well. And also you can use, as I told before, Wireshark for collecting statistics. And of course, one of the principal is to check the traces log, which is, I know it's a bit annoying at the beginning, but by grabbing and finding the tools, it is one of the most trends tool for checking what is happening in your simulation. So why we would like to re-implement models and tools for an open source implementation. So we would like to be as much as close as possible to the real scenario. So we would like to be make NS3 able to as much as close as possible to real implementation. So in order to make it, we can rely on this packet functionality, so we can spill out packets, and we can use pickup traces. So we can actually understand whether our simulation is working correctly and integrate it with the real code. As I told you before, there is two different modes for integrating NS3. The first one is Network Simulation Cradle. So it's a Linux TCP code for NS3, but it is not anymore maintained. So it works, but probably with the last version there might be some problem. But what is very interesting tool is the direct code execution. So in this case, you can link NS3 with real user spaces or real application and kernel code. This is a very powerful tool. So you can integrate, for instance, I don't know, a Skype application, or integrate your simulation in a real network, for instance. For instance, this is an example of an emulation with testbed integration. So we might have our NS3 simulation that runs a node and a specific net device, so where we can spill out our packets and then use real device for actually transmitting data. And so in this case, what we will have an application running on NS3, and then a real network that provide you how your application works. This is, for instance, is quite useful for testing routing protocols in real networks. So you do not have to port your routing protocols to actual devices, but you can run in NS3 and then spill out packet and inject packet in real devices, such as Wi-Fi cards or sensors. This, for instance, is an example of this kind of integration in the framework of an European project called Combo. We have been able to extract packets from the E node B and send it through the adrenaline testbed, which is a testbed on fiber optics. So what we have been able is to use interconnect a real LTE, an emulated LTE network with a real transport network based on fiber optics. So, and in order to connect the antennas to the core part of the LTE network. So this is an example of this kind of solution. Another possible and important solution, an important functionality for what the direct code execution framework is the network emulation. So in this case, what we will have is that we can create different instances of the NS3 in order to have different nodes, in order to emulate different nodes on the network. So we can have, for instance, sensors or user equipment in LTE. We can have the node B in another device, and we can have the gateway in another device. So these are placed in different virtual machines, running NS3 and exchanging packets. So an example of a, let's say, of a solution going on this side, but not actually this one, is, for instance, what has been done in Crown project, and what we will do in Flex 5G, where, for instance, in this project, what has been done is to interconnect the MAC layer of an LTE E node B to real devices. In this case, these FPGAs. In our case, another type of PGA. So we have a real, an emulated LTE network with interconnected at the MAC layer with real devices, with a real implementation. This is quite powerful because you can, for instance, play with new standards, for instance, playing with 5G signals instead of using standard LTE ones, and see what is happening in your network. So it's a step for integrating testbed and prototype, and for a fast prototyping, very, very powerful. So closing a bit the NS3 part, the general NS3 part. So NS3, as I told you, since it's a very wide community, it has been able to among the years to provide a very, very huge documentation. So you have tutorials online, manuals, and also a very extensive model library docs. So if you would like to have some information on the Wi-Fi module, you will have just to check online. There's a lot of libraries, examples. For instance, in order to being able to setting up your network very easy. And also, it provides a Doxygen documentation, very, very powerful, in which you can just type your object name, and it returns you the actual documentation, like in I don't know whether you're familiar with the Eclipse environment. The developer environment is very similar in this case. So if you would like to know what is some information about your MAC protocol, it's just a matter of typing it, and it returns all the information. This is all available on the web, so you don't have to print or pay something. It's just open source, and also can be either generated from the source, so you do not have to rely on any web. It's just integrated in the code. So there is also a wiki in order to have information on events, on the releases. Usually there is a couple of releases per year, or 2-3 releases, depends on the year, in order for updating the code, integrating bug fixes, and this is included in the wiki. In the wiki there is also many how-tos in order to, for instance, how to implement, how to set up a network, how to set up how to integrate, for instance, Eclipse with NS3, and so on and so forth. There's a very huge number of how-tos for helping you. And of course, there is 2 mailing lists. This one is very, very active, actually, and in which you can usually ask more or less whatever you want. Of course, according to some rules, you need to ask something that is coherent, and in providing, let's say, a detailed request. Is not a matter of how can I set up a network, because usually they redirect you to the tutorial if you provide very, let's say, open question. But there is a very huge number of people that usually answer, I would say, in a couple of days, 2-3 days. Of course, this is done based on a voluntary work. It's not a matter of no one is paid, so you cannot. It's not a matter of one day answer, but usually in a couple of days you usually have answer. And also there is a developer list if you would like to have more information, more detailed information on what is happening from developing perspective. If you would like to provide a patch, you find a bug, you would like to provide a patch, here you can talk with the developers, or they can put in contact with the maintainer of the object of the code you would like to provide a patch. These are all the informations, let's say. So now we're supposed to move to LENA. So if you like that, if you have any question first on NS3, so this might be, we can either. Yeah, definitely. You can. I mean, there's been actually a work for interconnecting some MATLAB code in the protocol stack. So, for instance, implementing the transmission chain of Wi-Fi, if I remember correct. But this does not work very well because MATLAB is quite. But definitely for post-processing data, it's very powerful tool, MATLAB. I'm usual to use MATLAB for post-processing data, or Octave, for instance. And definitely, usually in NS3 you can generate TXT files, so MATLAB or matrices, so you can very easily post-process it with any MATLAB or Octave tool. So this is a good solution. And actually, MATLAB is also used in LTE for generating the fading traces. So with MATLAB, you can generate TXT with matrices. And there is some work on to this respect. As I told you, we have done in the framework of the LENA project something similar just for fading traces. There were people working more in depth, also integrating the actual channel matrices. There is people working on ray tracing, providing with MATLAB a ray tracing solution, but it's not officially integrated in the NS3 framework. And so, in principle, you can. Yeah, and there's many people doing this, but in the standard modules like Wi-Fi, LTE, there is no such a kind of integration. So it's possible, but there's no actual implementation in this. The main problem to this respect is usually the computational complexity. When you plug MATLAB with NS3, usually you slow down NS3, and then if you have to simulate huge networks, it might be a problem. But if you would like to use NS3 like a system level simulator, so you do not have very high constraints or high requirements of network topology, you can actually do it. Actually, regarding the wireless sensor, at the beginning, I don't know why people, probably due to the fact that NS2 supports a very huge number of routing protocols for wireless sensor, many people they stick to NS2. Now, especially during the last year, the work on wireless sensor networks in NS3 has been improved, and there's a lot of protocols also for NS3 now. So it seems that this wireless sensor community is moving slowly to NS3. Of course, probably since they had a huge, let's say, inertia for the amount of protocol already done in S2, this took a bit more, but now they're moving. And in fact, we have, during last Google Summer of Code, we had a project on low rate WPA network. There is also some work on underwater acoustic networks. So there is. No. It's very, let me say, if you were to do from a legal perspective, very similar to the topology you are describing. Of course, it depends on the wireless technology you are using. For instance, for LTE, it's a bit more complex because you don't have just 2 nodes, but you need to in your scenario, you have to also to put the eNode B, the user equipments, the core of the network. But definitely for instance, for Wi-Fi network, it's just a matter of put the 2 nodes and connect them. Or even if you have fixed networks, you just to put the 2 nodes and the point-to-point link, so what you call bus. And then, of course, what I see is a very interesting work for integrating smart grid concepts in an S3. Definitely might be very interesting. There is for working with for Ethernet scenario, very simple scenario. There is a few there is a few graphical interfaces that works very well. Of course, as soon as the scenario becomes more complex, like in LTE, they started not working because it's much more complex. You have a huge number of protocols. But for implementing simple topologies with Wi-Fi, for instance, there are a few tools that works perfectly.
So what should we do? I mean, we have the coffee ready, so
I can either start or depends on.
I mean, as you wish. Essentially, what do you prefer? Do you prefer to have the break now and then we continue with the next part, or we start for 15 minutes, 20 minutes?
For me, it's the same. I can start with general issue and then move,
Okay,
or
so
I can
let's
stop.
follow the agenda. So we
Okay.
continue for 15, 20 minutes.
Okay.
At 11 we'll start with
Okay, so now let's move to the LENA project. Actually, the LENA project is the name of the LTE module in NS3. So we started with working on NS3 and LTE in 2010 during Google Summer of Code, in which Giuseppe Piro, a very good student from Polytechnic of Bari, started the implementation of the LTE framework. Then we have been contacted by Ubiquisys, an SME from UK, which implements small cells, so small eNode B for like called femtocells at the time, the one that you should use at home, for creating a new simulator based on the NS3 and from this. Based on the code generated from the Google Summer of Code, for design and test self-organized network in order to allow LTE vendors for testing their solution and their algorithm. So the main idea was to actually have a tool product-oriented, so something that is not only a simulator for simulating your network, but actually a code that allows you to test the real code in the simulation, have an accurate model of the protocol stack, and also consider the specific channel physical layer models for macro and small cells, the one defined, for instance, for 3GPP, the standard body that involved in the definition of the LTE standard. So in order to do this, we started from an industrial API, which is called Small Cell Forum. It's a body that generates some APIs for the femtocells, so the small inode B. And this defines a scheduler interface specification in which you have all the information for interexchange the data from the scheduler, so from the core of the allocation system of the LTE, placed in the inode B, the antenna part of the telecommunication system. So the main idea is to have an open source simulator, so something that was developed in an open community like an S3, in order to foster the adoption and have contribution from many people. This, of course, in order to helps in building confidence and trusting on the simulation model. So we do not have our own LTE model, but with something that is well tested and well recognized from our research community. And of course, in order to create a reference platform for evaluating, and of course using the GPL license in order to promote the interexchange of the simulation. Let me say that this is a paradigm that we are also pushing now in moving from small cell forum even to 3GPP, because now we have been working last summer with Wi-Fi Alliance for evaluating the interworking between Wi-Fi and LTE in the unlicensed band. So actually, we are working jointly with Wi-Fi Alliance for providing results in 3GPP meetings in order to show how LTE works with in the same band of Wi-Fi. And the idea is to promote NS3 as a candidate platform for being used in this kind of test in 3GPP. So what is the task of LENA? What's at that stage, 5 years ago, was the idea of LENA? Is, of course, to design what is called the schedulers in LTE. So how LTE schedule the resource to the user, both from downlink and uplink perspective. So test radio resource management algorithm, also inter-cell interference coordination solution, how different antennas interfere with each other, doing some load balance and mobility management, so how to move user in order to have a balanced network. Also check heterogeneous network solution, so having devices like your mobile, having that have Wi-Fi and LTE solution. Test, of course, end-to-end quality of experience statistics. So in order, this solution allows you to have for instance, from your user equipment up to the core, and so you can have the actual end-to-end quality of experience performance for voice over IP application, video application, considering, of course, all the whole protocol stack, so also the TCP and so on and so forth, which is usually quite difficult to have in standard network simulation tools. And also in general, let's say, multi-radio technology solution and cognitive system, for instance. So, system with where LTE can coexist with other radio access technologies, like Wi-Fi, Bluetooth, Zigbee, and so on. So in general, what is studied in 802.1121, so this kind of solution where you can have different antennas, like for instance in machine-to-machine, that you might have sensors with different devices. So from high-level perspective, the requirement was to support, of course, end-to-end quality of experience solutions. So we would like to test what is actually the user experiencing. It's not just a matter of saying we have this throughput, we have this delay, but it is a matter of also to have we have this quality, or voice quality, or picture to signal, picture SNR, for if you will have some video application. And to test, of course, also radio level performance, because you also need to know what is happening in your telecommunication network in order to understand why something is not working from application perspective. So LENA allows prototyping for QoS-aware packet scheduling. So you can allocate your resources in a QoS-aware fashion. So radio resource management, from high layer perspective, you can play how provide connection to the user and how manage the power and so on and so forth. Intercell interference coordination, so how control the interference, for instance, between small cells, so small antennas and big antennas in an LTE network. Also self-organization solution, which are very important in LTE, especially in the next releases, where the self-organization framework will be pushed a lot, like in release 11 or 12 of LTE. And also for cognitive dynamic spectrum access, because as you well know, the spectrum in LTE is licensed spectrum, so you need, and there is a huge need of spectrum in order to increase the capacity of the network. So solutions like dynamic spectrum access or cognitive spectrum access are very important in LTE networks. So the scalability requirements, we started working with few from tens in node B up to hundreds of node B, and from hundreds UEs up to 2,000 UEs. So you can test, let's say, huge network, but not, for instance, a country network. You cannot test the whole Spain network or the whole US networks, but definitely you can test from rather huge networks.
In this case, for example, thinking of the smart grid, you may want to simulate a network with thousands of smart meters, for example. Is there any alternative to increase it? I mean, maybe by simplifying the node architecture, I don't know, how do you see that? I mean, would it be possible to make a simulation with 100,000 meters?
With LTE, you mean?
With LTE simulator?
Right now, it will be not possible, of course, but there's a lot of, well, we have been investigating how to do it, and of course there is possibility, because the main problem, as I show you later, is the high accuracy in the physical layer. Since usually this kind of devices has a very simple physical layer, we can, by reducing the accuracy of the physical layer, you can speed up the simulator and also reach more users. But of course, this will require us some effort for.
I mean, there is no fundamental limit.
No, actually, it's just a matter of find out the way of reducing this kind of complexity, which we need for satisfy our requirements. But if we remove some radio level performance requirement, of course we can extend the scenario to many more users. So, as I told you, in fact, the simulation is a trade-off between the detail of the model, the implementation complexity, and especially the runtime scalability, so what we were discussing. So in this case, since we need to satisfy a small cell scenario where you might have a few macro node Bs interfering with the small cells, we realized that this was our good trade-off for having a reasonable runtime duration of the simulation, but with also a reasonable detail of the model. And also minimizing the difficulty in using the simulator, because when you start using industrial API, you need to actually, it's not so easy will become not so easy to implement, especially for new users, for students that have to know all the APIs. So we try to be as much, let's say, to reduce as much as possible the usage of this API for helping people for working on this simulator. So some important design choices. Let's go a bit more in depth in what we use as design choices. As I told you before, we use the femtoforum, now this called small cell forum scheduler API. So the scheduler is the core part of the antennas where, based on user request, the network decides how to schedule packets, how to schedule user. So we design the simulator around this component. From radio perspective, we use the resource block, which is the smaller resource assignment type from Mac perspective. So if you're familiar with not familiar with LTE, it's a bunch of 12 carriers in 1 millisecond long symbol. So we realized that for symbol level model was not affordable for this kind of simulation, because in order to have the scalability that we need, we will not go up to symbol level. And we implement some specific channel and physical error model, some abstraction, especially in the physical model, in order to have realistic performances. From moving on the protocol stack, we have, of course, a realistic RLC. RLC is the protocol that manages the connection from the user to the actual connection from the user to the antenna, and all the protocols above. This allows us to integrate with the IP networks, IPv6 and IPv4, and to have end-to-end quality of experience performances. The control plane, so how LTE control the whole network. We have the LENA implements a realistic RRC model. RRC is the actually radio resource control model. So, but we have, from core's perspective, we simplified a bit the models. So the core is you can do all the core's functionality like handover, attachment, and so on and so forth, but they do not have a detailed model exchanging realistic packets, as I will detail before. And of course, finally, we focus on connected mode. So the LENA works on RRC connected mode. So in principle, users works to be connected to the node B. So when they do not have a signal, they try to connect to another node B, but they do not stay in idle without doing nothing. Of course, they can do nothing in case they do not have traffic. They are where they will, but from LTE perspective, they will be connected. This is the standard LTE solution. So as I told you before, we have the user equipment that are nodes, what I told before, the standard necessary nodes. We have the antennas, called the eNode B in LTE. And then we have what is core, LTE core, the APC, evolved packet core, which is with MME, the mobile management entity, and the gateway for going to the internet. So these are the interfaces these are the red interfaces in red, while in blue we have the X2 interfaces, and the S1 interfaces, the one with solid line exchange real packets. The one with dotted line exchange is just a logical connection. So they do not exchange real packets, but they are just system calls. But, so you cannot, for instance, keep track with Wireshark of what is happening in the network here. You need to rely on traces, on simulator traces. For instance, what we have done, what I explained before, what we have done in Combo, we split these two links, and we put here a fiber optic testbed. So we connect the EPC with fiber optic to the core part of the network. This is the end-to-end data protocol stack. So as you can see here, the stack.
Sorry for interrupting again. Can you go back one slide?
Yep.
So are you aware of any ongoing work to also include the communication between devices? So device-to-device communication?
Well, through so directly device to device, there's no right now there's no active working on this. We are. Yeah. So, if someone would like to start working on this, of course, that will be very interesting. And as I can anticipate. Of course, we are usual to work with Google Summer of Code framework. So one possibility to implement this and also be remunerated, or let's say have something visibility, or have someone helping you, for instance, is the framework of Google Summer of Code. In spring, usually each spring, usually NS3 gets some grants from Google for get some students and mentor them in order to implement some project, therefore extending the NS3 framework. This year we have been doing some career aggregation. We have been working in the past year on scheduling, and actually the whole LENA project started from a Google Summer of Code project. So
this kind of development
can be, it's a good framework because it allows you to have some milestones, some money, of course, both to you and to your mentor. So I definitely, I feel very happy with this kind of framework. And of course, usually during springtime, hopefully also this year, Google provides us a few slots, usually are up to 3-4 slots. What we do in general is to provide some project, but if some student comes with a project, we might find usually in the NS3 consortium, we might find a mentor, someone that helps in implementing it. And actually this year there was one guy working, for instance, on 6LoWPAN network. What is actively working now in the framework of Combo project is to also generate packets in these three interfaces. So remove this logical connection in order to be able to split these two entities. Be able to split, for instance, the node Bs, the antennas, to the core part of the network. So this is the end-to-end protocol stack. As you can see, we have the LTE radio protocol stack. So from UE side, the RLC, the MAC, the physical layer. The PDCP is the controller of the connection, the IP network, the TCP, and application. Here we have the end-to-end connectivity, so up to the remote host. Node B has two different, for instance, in an example of multi-radio access technology is the Node B, where we have the radio protocol stack, the LTE radio protocol stack from one side, and standard, usually a standard Ethernet connection or fiber connection, let's say a point-to-point link connection for connecting to the core part of the network. And this is the typical, the data plane one. So this is the going a bit more in details. This is the standard architect data flow in downlink. So here we have the node. So in downlink we start from the internet. So the packet enters to the core part of the network. They are tunneled in order to maintain the IP characteristics. So the inner flow packet. So then they go through the routing part of the core, and they move to the node B. And in the node B, they tunneled, and then they can reach the user equipment. So this is a standard data plane architecture. This is an uplink, which is very similar. And this is the protocol stack from data perspective. At the UE side, we have this is the LTE net device. So this is this part of the network. Sorry, now we are talking about this part, these two parts. This is the data plane. So we have the LTE net devices that can send and receive packets. The user equipment NAS, so the non-access stratum, which is a layer that devoted to manage the end-to-end connectivity. This is the UARLC, managing the actual connection of the different connections, and then the different connections are managed. So the different bearers in LTE with LTE naming are managed through the PDCP and RLC protocols. And then we have the MAC layer. That's usual to do some scheduling, fragmentation, hybrid queue, and so on, and the physical layer. From Node B side, it's almost the same. So what we have and the layer above, also the EPC part. So it's very similar. And also, as you can see, The scheduler, it's placed here, since we have just, since it's in charge of the node B, of the antenna, to schedule out the resources in the system. Either the uplink and the downlink one, of course. So this is the channel architecture. So let me check. We can stop. So if we like, we can stop. It's 11. And then I can start with the physical layer.
Excellent. Okay, so let's have the coffee now.
If you have any question on this part, feel free to stop me if there is too much acronyms. I'm quite LTE, let's say, biased, so sorry if you have some question. Feel free to interrupt me whenever you want for asking something, or if I forgot to explain an acronym, or